Every year, the world decommissions dozens of nuclear submarines, steel giants weighing over 10,000 tons that once carried reactors pumping out hundreds of megawatts. But what happens to these steel whales when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that can drag on for months? In this video, you'll see a process where temperatures hit 15,000 degrees Fahrenheit, and a mistake isn't measured in seconds, it's measured in centuries. And if you stick around till the end, you'll find out what the armor of these underwater giants actually becomes. The process of transforming a fearsome nuclear submarine into a pile of safe scrap begins with an operation that is dealing with the spent nuclear fuel. Picture this. The boat enters a special enclosed dock, and around it unfolds a genuine scientific laboratory. This isn't just dismantlement, it's a battle against invisible radiation that will last not days, but months. Before the first torch touches the hull, specialists must empty the reactor. Inside the core are fuel assemblies that for decades sustained the life of this monster. Using remotely operated manipulators and giant cranes, these assemblies are carefully extracted through technological openings. Each of these fuel rods emits a lethal dose of radiation, so they're immediately placed into massive lead container cocoons with walls more than 10 inches thick. When the fuel's removed, it's the reactor compartment's turn. This massive section of the boat weighs over 1,500 tons. Engineers don't disassemble the reactor piece by piece. That'd be way too dangerous because of the induced radiation in the metal itself. Instead, they just cut out an entire chunk of the submarine. This block gets welded shut with steel plates, turning it into a sealed capsule. This nuclear package gets loaded onto a special barge and sent on a long journey to permanent storage sites. In the US, for example, that's the famous Hanford site. There, these reactor blocks get lined up in deep concrete trenches under the open sky, where they'll sit for the next 300 years until radiation levels drop to safe values. Only after this radioactive core has left the dock can we say the submarine has become just a very large and very tough ship. Deactivation. That's the longest and most exhausting phase, turning a nuclear submarine from a radioactive fortress into ordinary scrap metal. When the reactor compartment's already cut out and shipped off to storage, the work's just getting started. Thing is, decades of coolant circulation have left their mark on thousands of feet of pipes, pumps, and heat exchangers. Radioactive isotopes literally eat into the metal walls, creating induced radiation. First thing, a team in sealed suits conducts a complete scan of every inch of interior space. They're hunting for hotspots, places where radiation levels exceed the norm. Then chemical flushing of the systems begins. Aggressive acid and alkaline solutions get pumped through the primary circuit piping to wash away the radioactive buildup from the walls. This liquid's then collected in special containers, filtered, and converted into solid waste for disposal. But chemistry doesn't solve everything. Some components, valves, gates, and filters, have to be removed by hand. Each piece goes into a lead-lined box. Special attention goes to the biological shield, massive slabs of lead and polyethylene that surrounded the reactor. These can weigh hundreds of tons, and each slab has to be carefully extracted and decontaminated using ultrasound or mechanical scrubbing. Only after thousands of air samples and surface swipes show zero hazard does the dock get the green light for regular workers. Now it's no longer a nuclear site, just a complex engineering puzzle waiting for final cutting. It's meticulous work, where every step gets logged in protocols, because safety in the nuclear industry isn't measured in minutes. It's measured in centuries. After months of fuel removal, reactor extraction, and meticulous decontamination, the submarine is finally ready for its final dismantling. But don't think this is going to be a quick process, like cutting open a tin can. A submarine hull isn't just metal. It's an alloy built for war, capable of withstanding the colossal pressure of water at depths of thousands of feet and even torpedo blasts. Ordinary hydraulic shears won't cut it. Enter tools that look like weapons from sci-fi movies. we see massive cutting platforms rolling up to the hull. The first tool, plasma cutters. They create a jet of ionized gas with temperatures exceeding 15,000 degrees Fahrenheit. That's multiple times hotter than the surface of the sun. Under this flame, even the toughest steel, 3 to 4 inches thick, melts in seconds. But this method is slow and demands constant control. Every move of the torch creates a trail of smoke and sparks that fly dozens of feet. Another, even more striking tool, oxygen lances. These are long metal tubes packed with steel rods. Pure oxygen is pumped through them at high pressure. The lance is ignited, and the oxygen begins oxidizing the steel, generating temperatures up to 7,000 degrees Fahrenheit. It's like a controlled explosion. The oxygen lance burns clean through the metal, leaving behind a glowing seam. It's faster, but it takes serious skill to avoid damaging internal structures. The work begins at the bow and stern, gradually advancing towards the center sections. Workers handling the torches are protected by special suits and masks that filter the air, because the fumes from cutting contain microscopic metal particles. The hull gets sliced into massive cylindrical sections. Each one of these sections, representing a chunk of hull roughly 20 feet long, can weigh up to 2,000 tons. These steel rings, which until recently were part of a fearsome war machine, are now carefully hoisted by giant cranes and stacked in specialized zones where they'll await sorting and remelting. This process isn't just cutting. It's the final act of transforming a military giant into raw material for a new life. After the gigantic 2,000-ton hull sections are cut down into smaller, transport-friendly fragments, a stage begins that determines the future fate of this metal. This isn't just tossing scrap into one pile. Every piece of steel that once withstood the pressure of ocean depths goes through rigorous intake inspection. The first and most critical stage is the final radiological check. Despite prior decontamination, each fragment gets scanned again with ultra-sensitive dosimeters. Specialists hunt for the tiniest traces of isotopes that might be hiding in microcracks or weld seams. If the device signals, that piece gets immediately isolated and sent back for recleaning or special burial. Only clean metal receives a safety certificate, allowing it to leave the shipyard and head to the steel mill. Next comes sorting by chemical composition. HY80 and HY100 grade steels contain valuable additives: nickel, chromium, molybdenum. It's a real treasure for metallurgists. These elements make the steel incredibly tough and corrosion resistant. At the plant, these plates get loaded into giant electric arc furnaces, where under the influence of electric discharge with power measured in tens of megawatts, the metal transforms into a liquid sun. Temperature in the furnace reaches 3,000 degrees Fahrenheit. During the melt, lab techs constantly take samples to adjust the alloy composition. Yesterday's battleship conning tower plating could become the foundation for bridge supports spanning a major river, where you need colossal resistance to vibrations and loads. Or it transforms into rebar for a skyscraper in the heart of a megacity, standing tall for centuries. Don't forget to hit that like button and subscribe, folks. Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is coltan, a dull black rock that looks like an ordinary river stone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. A laptop, up to 100. Gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives. The bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day. More than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor, or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries. Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous, corruption thrives, tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. Thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse, when natural resources become not a blessing, but the cause of endless wars and suffering. The roof of SoFi Stadium in Los Angeles weighs 31,000 tons. which is roughly the same weight as the entire Eiffel Tower sitting on top of a football field. And somehow this massive structure stays suspended in the air, covering 70.2 acres without a single support column underneath. That roof is made entirely of steel beams, each one precisely engineered to carry thousands of tons of weight while allowing the structure to flex and move with California's earthquakes and temperature changes. So how do you actually make steel strong enough and precise enough to build something this massive? Where does all that metal come from? And how does it go from raw iron ore to a beam that's holding up 31,000 tons of roof? Today, we're going inside the factory in Ohio, where every single one of those steel beams was made. And I'm going to walk you through the entire journey from the moment iron ore arrives at the plant to the moment a finished beam gets bolted into place 70 feet above the field in Inglewood, California. The factory is the Nuclear Steel Mill in Marion, Ohio, which is a mid-sized industrial town about 40 miles north of Columbus. And when you pull up to this facility, you see a sprawling complex covering over 1,000 acres, where some of America's largest construction projects get their structural steel. What makes this particular plant special is that they specialize in something called wide flange beams, which are those massive W-shaped steel beams you see in skyscrapers and stadiums. And the entire SoFi Stadium project was manufactured right here at this one location. The raw materials start arriving by train several times a week, with deliveries of about 10,000 tons of iron ore coming from Minnesota's Mesabi Range, along with limestone from Michigan quarries, and metallurgical coke that's been processed from coal. All of these materials get stockpiled in massive outdoor yards, where you can see mountains of reddish-brown iron ore sitting next to gray limestone piles. And from here, everything gets moved on conveyor belts into the main building where the transformation begins. At the heart of the facility, there's a blast furnace that stands 12 stories tall. And even from the outside, you can feel waves of heat coming off the structure, because inside the temperature is running at 3,200 degrees Fahrenheit. The way it works is actually pretty straightforward. Iron ore, limestone, and coke get loaded into the top of the furnace while superheated air gets blasted up from the bottom at speeds over 600 miles per hour, creating this incredibly intense chemical reaction. What's happening inside is that the extreme heat is literally ripping iron atoms away from the oxygen and other elements they're bonded to in the ore, and all the waste material rises to the top as liquid slag that gets poured off and ends up being used for cement production. The pure molten iron sinks to the bottom and collects in this glowing orange pool that you can see through special observation windows. And every few hours, they tap the furnace and the liquid iron flows out into these enormous ladles that each hold about 250 tons of metal. Those ladles get picked up by overhead cranes and moved about 60 feet over to the next building, where the iron gets converted into the specific type of steel needed for structural beams. In the steelmaking building, there's what's called a basic oxygen furnace. And this is where the chemistry gets really precise, because the difference between iron and structural steel comes down to exact percentages of carbon and other elements. They pour the molten iron from the blast furnace into this massive vessel, and then they blast pure oxygen into it at supersonic speeds, which ignites the carbon dissolved in the iron and creates these huge flames shooting 30 feet into the air. The entire process takes about 20 minutes, and during that time, they're constantly testing the composition and adding precise amounts of other elements like manganese and silicon to get exactly the right mix. For structural steel, like what's used in SoFi Stadium, they need the carbon content to be around 0.2%. If there's too much carbon, the steel becomes hard but brittle and could crack under stress. But if there's too little carbon, it becomes too soft and will deform under the weight of the structure. The margin for getting this right is incredibly tight, because one small mistake at this stage means the steel won't meet the structural requirements and can't be used for a project like SoFi, where lives depend on it. From the oxygen furnace, the molten steel flows into continuous casting machines, where it starts taking solid form, pouring into water-cooled molds that shape it into thick rectangular slabs called blooms that are about 10 inches thick and 3 feet wide. These blooms come out still glowing bright orange at around 2,000 degrees Fahrenheit, and they immediately go into reheating furnaces where they're brought back up to exactly 2,300 degrees before heading to the most important part of the whole process. The rolling mill is where these thick blooms of steel get transformed into the distinctive W-shaped beams that you see in construction, and when you watch this process, it's absolutely incredible. The glowing steel passes through a series of massive rollers, and each set of rollers has a different shape cut into it that progressively forms the W profile. In the first pass, the bloom gets compressed and starts elongating, and you can literally see the metal flowing like thick honey as these rollers that are applying thousands of tons of pressure reshape it. After about 12 passes through different roller sets, the distinctive W shape starts emerging. You've got the wide horizontal flanges on the top and bottom that provide strength against bending, and the vertical web in the middle that provides stability against twisting. For SoFi Stadium, they needed beams ranging from 14 inches deep for smaller supports all the way up to 44 inches deep for the main roof structure, and each size requires a completely different set of rollers. The precision required here is absolutely critical, because these beams need to be accurate to within 1/8 of an inch across lengths that can be up to 75 feet long. After the beams come out of the rolling mill, they're still around 1,000 degrees Fahrenheit, so they go through a controlled cooling process where they're laid out on cooling beds and air-cooled down to room temperature over the course of several hours. Once they're cool, each beam goes to the fabrication area where they get cut to exact lengths using massive saws with carbide-tipped blades, and this is where the beams start being customized for their specific locations in the stadium. For a project like SoFi, every single beam has a unique set of holes that need to be drilled at precise locations for the bolts that will connect it to other beams. And these hole locations are programmed into computer-controlled drilling machines that can position a drill bit accurately within 1/16 of an inch. Some of the main roof beams have over 200 holes drilled into them, and each hole has to be exactly the right diameter and positioned exactly right, because when you're connecting beams that are holding up 31,000 tons, even a small misalignment creates dangerous stress concentrations. After fabrication, every single beam goes through the most rigorous inspection process you can imagine. And there's a very specific reason why this quality control is so incredibly strict. On July 17th, 1981, the Hyatt Regency Hotel in Kansas City had these suspended walkways in the atrium, and during a crowded party, one of the walkways suddenly collapsed onto the one below it, and both of them crashed to the floor. 114 people were killed, and over 200 were injured, and the investigation revealed something absolutely terrifying. The original design had called for the steel hanger rods to run continuously from the ceiling through both walkways, but during construction, someone made what seemed like a minor change. They used two separate rods, with the upper walkway hanging from the ceiling and the lower walkway hanging from the upper one. This seemingly small modification doubled the load on the connection points, and under the weight of the crowd, the connections failed catastrophically. That single decision to change how the steel components connected to each other became one of the deadliest structural failures in American history. That tragedy completely transformed structural steel quality control. Today, at the Nuclear Submarine plant, after fabrication, every beam goes through ultrasonic testing, where sound waves pass through the entire length of steel, detecting any internal flaws or cracks as small as 1/10 of an inch. They also do magnetic particle inspection on every connection point and weld to make sure there are no surface defects, and dimensional inspection with laser scanners to verify that every hole is in exactly the right place and every beam is exactly the right length. The rejection rate for structural steel destined for major projects is around 8%, which means roughly 1 out of every 12 beams that makes it through fabrication never leaves the plant because it doesn't meet specifications. After what happened at the Hyatt Regency, nobody in the structural steel industry is willing to take chances with quality control. The beams that pass inspection get loaded onto specialized rail cars for the journey to Los Angeles, and we're talking about a pretty massive logistics operation here. For the SoFi Stadium project, they shipped over 4,000 individual steel beams, weighing a total of 31,000 tons over the course of about 18 months. With trains leaving Marion several times a week. The route takes them west through Indiana and across the Great Plains, then through the Rocky Mountains, and across the desert into Southern California, a journey that takes about 5 days. When the trains arrive at the rail yard in the City of Industry, just east of Los Angeles, the beams get transferred onto specialized trucks with extendable trailers because some of these beams are 75 feet long and weigh over 15 tons each. The trucks then have to navigate through LA traffic to get to the construction site in Inglewood, and for the largest beams, they can only move them at night when traffic is light, and they can get police escorts to manage the oversized loads. At the construction site, the real challenge begins because these beams need to be lifted into position and connected together 70 feet above the ground to form the roof structure, and the margin for error is essentially zero. The construction crews use massive mobile cranes that can lift up to 500 tons, and each beam has to be maneuvered into place so that all those pre-drilled holes line up perfectly with the holes in the beams it's connecting to. The connections use high-strength bolts that are torqued to very specific tensions, typically around 700 foot-pounds, and every single bolt gets checked multiple times because these connections are what's holding the entire 31,000-ton roof structure together. The roof design actually allows for up to 6 inches of movement in any direction to handle thermal expansion and seismic activity, which means the steel needs to be strong enough to carry the weight, but also flexible enough to move without cracking. When the Hyatt Regency walkways collapsed in 1981, structural steel was already a mature technology that had been used successfully for decades. But that disaster taught the industry that you can never assume anything about connections and quality. Today, 44 years later, SoFi Stadium stands as proof of how far the industry has come. 31,000 tons of steel suspended over 70 acres, engineered to survive earthquakes and support the weight while still allowing the structure to flex and move. You've now seen how iron ore gets transformed at 3,000 degrees into molten steel, how that steel gets rolled and shaped into precise W-beams, why 8% of production gets rejected before it ever leaves the factory, and how every connection point gets inspected multiple times because the lessons from past tragedies are built into every step of the process. If you found this interesting, subscribe to see more deep dives into how the massive structures around us actually get made. Thanks for watching. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle
The lightest
lubricating
fractions
oils and
collect
heavy
at the top,
residues.
medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point, gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture, a process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of percent and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces, or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of %. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Every year, humanity pulls off the same impossible trick. We make ordinary rock flow like water and transform it into the foundation of cities, machines, and entire civilizations. But why does rock, where metal sometimes makes up less than a quarter, hide such colossal power? How does stone travel through hellish temperatures, oxygen explosions, and electric arcs hotter than the surface of the sun to become steel, copper, or aluminum? Behind the scenes of this process, there's a moment almost never talked about, a point of no return where the fate of metal and entire industries is decided. Watch this video to the end, and you'll discover what happens in that split second, and why, without it, the modern world simply wouldn't exist. It all starts with ore, rock that contains the desired metal in the form of chemical compounds with oxygen, sulfur, or other elements. Iron ore, copper ore, aluminum ore. They look like ordinary stones, maybe a bit colorful or heavy, but nothing special at first glance. The problem is that even in rich ore, the useful metal might only be 15 to 30%. The rest is waste rock that has to be separated somehow. Mining ore is already an epic undertaking. Open pit mines reach depths of over 1,500 feet and widths spanning several thousand feet. Massive excavators with buckets the size of a 2-story house tear away rock by the ton in a single scoop. Giant dump trucks with wheels as tall as a 2-story house and payload capacities of 300 to 400 tons haul ore to processing plants day and night. In a year, one large mine extracts tens of millions of tons of rock. The first step in processing is crushing. Massive rocks the size of a car enter crushers that break them down into fist-sized chunks. Then these chunks go into mills, cylindrical drums several yards long, filled with steel balls weighing several pounds each. The mill rotates, the balls drop, and pulverize the ore until it becomes a fine powder. The sound of such a mill, a rumble and clatter you can hear for miles. Now we need to separate the valuable minerals from the waste rock. Different methods are used for this. Flotation is one of the most popular. The crushed ore is mixed with water to form a slurry. Then special chemical reagents are added that make the surface of the metal particles hydrophobic, meaning they repel water. Then air is blown through the slurry, creating bubbles. Metal particles stick to the bubbles and float to the top as foam, while the waste rock settles at the bottom. Magnetic separation works for iron ore. Powerful electromagnets attract the iron mineral particles, and the waste rock just falls away. Gravity separation uses the difference in density. Ore with metal is heavier than waste rock, so on special vibrating tables or in water streams, the heavy particles settle while the lighter ones wash away. After enrichment, you get concentrate, a powder where the useful mineral is now 50 to 70%. But this still isn't pure metal. It's a compound with oxygen or sulfur. You need to remove these impurities and obtain the pure element. Let's take iron as an example, because it's the most common structural metal. Iron ore is mostly iron oxides, iron bonded with oxygen. To get pure iron, you've got to strip that oxygen away. This happens in blast furnaces, massive structures up to 100 feet tall and 50 feet across. A blast furnace runs continuously for years. It's loaded from the top in layers: iron ore, coke, and limestone. Hot air, heated to 2000 degrees Fahrenheit, gets blasted in from below. The coke burns. The temperature inside the furnace hits 4000 degrees. At those temperatures, carbon rips the oxygen away from the iron oxide. The iron melts and flows to the bottom of the furnace. The scale of the process is staggering. A single blast furnace consumes 3,000 to 5,000 tons of ore per day, about a ton of coke, and produces 2,000 to 3,000 tons of pig iron. That's iron with high carbon content, around 3 to 4%. The molten pig iron reaches temperatures around 4,000 degrees, a true river of fire flowing from the furnace every few hours. When they open the tap hole, an opening at the bottom of the furnace, the molten metal streams out in a brilliant yellow-white torrent into special ladles or channels. The light is so intense, you have to look through dark goggles. The temperature around it hits several hundred degrees, even from dozens of feet away. The air fills with the smell of hot metal and sulfur. But pig iron isn't steel yet. It has too much carbon in it. It's brittle and won't work for most applications. To make steel, you need to drop the carbon content below 2% and remove impurities like sulfur, phosphorus, and other elements. To do this, they remelt the pig iron in converters or electric arc furnaces. The oxygen converter is a massive pear-shaped vessel, as tall as a 5-story building, that can hold up to 400 tons of molten metal. The converter can be tilted to load pig iron and pour out finished steel. When the vessel is filled with molten metal, a water-cooled lance is lowered into it from above, and pure oxygen is injected under pressure. Oxygen is blown through the molten metal at a rate of hundreds of cubic meters per minute. Carbon burns off, creating an enormous amount of gases and sparks that shoot out of the converter's mouth like a volcanic eruption. The temperature of the molten metal rises from the energy released by burning impurities. The entire process takes about 20 minutes, during which 300 tons of pig iron are transformed into steel. Electric arc furnaces are used to melt down scrap metal. Massive graphite electrodes, up to 2 feet in diameter and several yards long, are lowered into the loaded scrap. An electric arc ignites between the electrodes and the metal, reaching temperatures up to 11,000 degrees Fahrenheit, hotter than the surface of the sun. Power consumption hits megawatts. A single furnace can burn through as much electricity as a small town. The metal melts, boils, violently reacts with added flux agents. Slag, a molten mix of oxides and silicates, floats to the surface of the metal and captures impurities. It's regularly tapped off separately. When the metal composition hits the target specs, the melt is poured into a ladle holding dozens to hundreds of tons. This process runs simultaneously at dozens of plants around the world, non-stop, 24 hours a day, 365 days a year. Every year, humanity produces around 2 billion tons of steel. That's roughly 550 pounds for every single person on the planet, including infants. 2,000 million tons. Try to wrap your head around that number. Non-ferrous metals are extracted similarly, but with nuances. Copper often occurs as sulfides, compounds with sulfur. First, the ore concentrate is roasted in furnaces at temperatures around 2,700 degrees Fahrenheit to oxidize the sulfur. Then it's melted at nearly 5,400 degrees, producing matte, an alloy of copper and iron sulfides. The matte is blown with oxygen in a converter, removing iron and residual sulfur, yielding blister copper at about 98% purity. But electronics and wiring need copper at 99.99% purity or higher. This is achieved through electrolytic refining. Blister copper plates get dunked into baths of copper sulfate solution, and an electric current runs through them. Copper dissolves from the anode and settles on the cathode as absolutely pure metal. Impurities either sink to the bottom of the bath or stay in the solution. The process is slow, but it produces the purest copper. Aluminum, that's a whole different story. It's the most abundant metal in Earth's crust, around 8%. But it's so tightly bound to oxygen that extracting it chemically is nearly impossible. Aluminum comes from bauxite, an ore containing aluminum hydroxide. First, bauxite gets treated with alkali under high temperature and pressure to produce pure aluminum oxide, alumina. Then this alumina gets melted through electrolysis in baths of molten cryolite at temperatures around 4,000 degrees Fahrenheit. A massive electric current, tens to hundreds of thousands of amps, runs through the molten mixture. Oxygen gets released at the anode and burns off, while pure aluminum settles at the bottom of the bath. Producing 1 ton of aluminum consumes roughly 15,000 kilowatt hours of electricity. That's about what an average apartment uses in a year. Aluminum plants get built near massive hydroelectric dams because you need cheap electricity in enormous quantities. One modern plant produces 1 million tons of aluminum per year and consumes as much electricity as a city of 1 million people. This is an industry that literally converts electricity into metal. Titanium extraction is even more complex. Titanium ore, titanium dioxide, first has to be converted into titanium chloride, then reduced with magnesium or sodium in sealed reactors at temperatures around 2,000 degrees. What you get is titanium sponge, a porous material that then gets remelted in vacuum arc furnaces multiple times to remove impurities. That's why titanium costs tens of times more than steel.